Bismillahirrahmanirrahim. Today, inshallah, we shall talk about two theorems that relate to tangents and circles. If you recall, previously we talked about chords, secants, and tangents. So here's circle O, and this is a chord that's in circle O with these two endpoints. If you recall, a chord is a segment that has 2 points that are on the circle as its endpoints. And here we have a secant right here. A secant is a line that kind of just goes through and through a circle. And here in purple we have a line. We can call this line M. And line M is tangent to a circle. That is, it touches the circle at only one point, and that point is called the point of tangency, like this. The remainder of the chapter is about various theorems that deal with chords, secants, and tangents. Okay, so here is a circle, circle Q, and I have a line over here. We can call this line M, that is tangent to circle Q. Now I'm going to draw the radius here from point Q to this point over here, the point of tangency, and we can call the point of tangency, let's call that P. So PQ is the radius of the circle. And by definition, a tangent line intersects the circle at only one point. Here's the first theorem over here. And let's just first digest the theorem, so to speak, and understand what it says, and then we can apply it. So let me read it off. A line is tangent to a circle if and only if. Now, if you recall, this IFF means if and only if. Now, what that means is that this statement is bidirectional. A conditional statement, if you recall, is an if-then statement. If such is the case, then such is the case. But if the statement is true also in reverse, in its converse, then, in other words, you can reverse the statement the other way around, then that's a bidirectional statement. And you hint that, or you convey that to the reader by saying if and only if. Now, if the statement has said a line is tangent to a circle if the line is perpendicular, that's a unidirectional statement. In other words, the statement would be true going forward, but not necessarily going backwards. But this terminology, if and only if, implies a bidirectional statement. It's true both ways. I'll tell you what that means also in a second in reverse. So a line is tangent to a circle if and only if the line is perpendicular to the radius at its endpoints on the circle. So let's look at that. So it's saying that this line, in our case, line M, is tangent to the circle if and only if right here, this particular angle is a right angle. So that's what this statement is saying. A line is a tangent to a circle if and only if the line is perpendicular. Right here, the line is perpendicular. This symbol means perpendicular. Now, you remember, this is perpendicular and this means a right angle. So this symbol means perpendicular and this symbol means right angle. So, again, a line is tangent to a circle if and only if the line is perpendicular to the radius. Now, here's the radius QP. And I denoted here R as the length of the radius here. So QP is the radius. Now every radius has two endpoints because it is a segment. So the endpoints of the radius here are Q and P. Now if I were to draw another radius over here, like this, let's call this, let's call this one K. Now Q and K would be the two endpoints of this particular radius. Now, if you recall, the word radius is singular, radii is plural. So, a line is tangent to a circle if and only if the line is perpendicular to the radius. So this line is perpendicular to that radius. If the line is perpendicular to the radius at its endpoint, not plural, endpoint right here. So the radius has endpoints, Q and P, because radius is a segment. And this line, if this line is perpendicular to this segment, to this radius right here, then it will be a tangent. So how do you know a line is tangent to a circle? Well, if its if at its point of tangency, right here P, and if you draw out the radius to the point of tangency, and that forms a right angle with the line, that line is tangent. Now, as I stated, this is a bidirectional statement. So if you read the converse of it, that is, if a line is perpendicular to the radius at the endpoint of the radius on the circle, then the line is tangent. So you can go backwards. See, a line is tangent to the circle if this happens, and then the converse would be if this happens, then the line is tangent. Okay, so this is a bidirectional statement. Now this theorem, and next one as well, gives rise to a whole host of very interesting geometry and algebra problems that are very commonly found on standardized tests and etc. So it's well worth understanding this theorem thoroughly. All this is saying is that if you have a tangent line, right, then if you draw out the radius from the center of the circle to the point of tangency, that will form a right angle between the radius and that line. And that has to be the case, see, because the shortest distance between a point and a line is the perpendicular distance in a plane. And you can actually say this qualification that in a plane, a line is tangent. So in plane geometry, okay, the shortest distance between a point and a line is the perpendicular distance. And so this has to be a perpendicular line. How do we know this is the shortest distance? Okay, well, we can show that because let's see, if you draw a line between the center of a circle and any other point on the line, will be farther than this point P, right? The reason for that is pretty understandable. Okay, for example, these are three separate points that are on the line M that's tangent to this. Okay, now these points, okay, will be the length of these segments will be larger than the radius, because to get there, first you have to go through the circle like this, that's the radius, and then some. To get there, here you have to go through the radius and then some. To get here you have to go through the radius and then some. So this is the only point, point P is the only point where you only, by the time you get to the end point of the radius, you don't have to go any farther to reach the point. Every other point is farther from the center. So you can see that the radius attaching to or ending at the point of tangency is the shortest distance between the center and this line, and therefore that's a perpendicular, that's a right angle. So this is intuitive, and you can provide a proof for this also, but today I just wanted to make sure that we understand this theorem. Simplistically stating then, the theorem says a line is tangent to a circle if and only if the line is perpendicular to the radius at its endpoint on the circle. Okay, in other simply stated, a line is tangent. If a line is tangent, then the radius that connects the center to the point of tangency will be perpendicular to that line. Before we go on, I'd just like to talk about the next theorem, and then we can apply both of these theorems in different problems. So here's the second theorem for today. It states that tangent segments from a common external point are congruent. Now, what does that mean? Well, let's give ourselves a circle here. Let's call this circle, I don't know, we'll call that Q. So I might as well call this one Q. This is circle Q. And if you have a point that's outside the circle here, it's like this, let's call that point, point S. And then if we draw two segments that are tangent, okay, you can have tangent lines and you can have tangent segments. Now this is a segment, see? So that is, it has two endpoints. It doesn't go forever. And a segment that is tangent to the circle like this, that's called a tangent segment. That's what this is. And if you have two tangent segments from the same point, like this, so here's S, and here's the other tangent segment like this over here. So here's a tangent segment here, and here's a second tangent segment here. It's not a line, it's a segment because it has two endpoints. tangent segment here. So if you have two tangent segments from the same point, so you can take any point that's external to the circle. So S is external, it's not internal. So if you take any point that's external to the circle, I could draw another one here. Here's a point, and I can draw tangent segments from there. Here's one from there, and those are the only two that you can make, see? So if you take any point, if you draw two tangent segments like this, okay, this theorem says that these two tangent segments will be congruent. So the two tangent segments, they're a pair. The two tangent segments from a common external point, in this case x, are congruent. That is, this segment will be congruent to this segment. We can let's label some of these points, and maybe we can call this point R, and we can call this point T. And if these two are tangent segments, then segment RS will be congruent to segment TS like this, okay? Or SR will be congruent to ST. So now this is actually pretty reasonably easy to prove from the theorem that we just had before. So if we could just draw the radii here, or the two radius. So I'm going to draw the radius over here. Let me draw a nice bright color here. So here's the radius QR, and here's another radius QT. Now I draw those out, and that's radius R. And here's R. And then we know just from the theorem before that tangents are perpendicular to the radius that connects to the point of tangency. So this is a right angle, and this here is a right angle as well. Then to prove that these two segments are congruent, that's RS is congruent to TS, it's reasonably easy, because what you can do is say you can just draw out this line, this segment here, QS. Now you have two right triangles over here, this right triangle over here and this right triangle over here, correct? So you have two right triangles, right? And then they have this common base over here, R, that's congruent. So this is congruent, right? And we're trying to prove that these are going to be congruent. And then they share a common hypotenuse, right? So hypotenuse, leg. If you remember, if you're proving a triangle is congruent, and if it's a right triangle, if the hypotenuse are congruent and one of the legs is congruent, then the two triangles are congruent. So these two triangles are congruent by hypotenuse, leg. And the third side here, the sides in question, the tangent segments, therefore, are going to be congruent by CPC, TC. Corresponding parts of congruent triangles are congruent. So that's the proof for this particular theorem. So going back as a review, so the theorem states basically that two tangent segments that arise from a single external point, two tangent segments that arise from a single external point are congruent. So these are the two theorems for today. All right. The first theorem, if you recall, was this one, basically stating that tangent lines are perpendicular to the radius that connects to their point of tangency. And the second theorem for the day is that tangent lines, two tangent segments from the same external point, are congruent. Now I'm going to do some examples with these questions to suggest to you how many questions you can be derived from these two simple theorems. Okay, here's a question. In this question, we're told that this angle over here, this central angle over here, is 130 degrees. And we're asked to find this angle over here, angle X. Well, how are we going to do that? Well, we already know that this is 90-degree angle, and this is 90-degree angle. And as you can see, that this is a quadrilateral. Right? QT, S and R, QT, SR, that's a quadrilateral. It's a four-sided figure. And we know that the sum of all the angles of a quadrilateral, just like a rectangle or a square, they all add up to 360 degrees. So if we were to add all of these angles, because this is a quadrilateral, and the sum of all the interior angles of a quadrilateral add up to 360 degrees, so these will all add up to 360. So 90 plus this 130 plus the other 90 plus x, they all must add up to 360 degrees. Now if you subtract all of this from the other side, so the x will be equal to 360 minus 130, and then minus 90, and I believe this comes up to be 50 degrees. So x is going to be 50 degrees. Okay, here's another question. Now, the question is, this is the given information. Segment ST is tangent to circle O at S. So this is a tangent segment ST, and it's tangent to circle O at this point S. Now that's important because then we can say directly that that's going to be perpendicular right there, and that's a 90-degree angle. And we're given that ST here is 24 and OT is 25. Now you noticed I didn't put a bar over here because when you do that, when you're saying segment ST, and if you thought the bar, you're talking about the measure or the length of the segment. So when you're trying to say the length of the segment, you don't put the little bar on by convention. Anyway, so ST is 24 and OT is 25. We're simply asked to find x, or what's the radius of this particular circle. Now, this is pretty easy question because as you can see, this is a right triangle, and if you wanted to do the whole Pythagorean theorem thing, you can do a squared plus b squared equals c squared, and x squared plus 24 squared is equal to 25 squared, and then you'll find that x is going to be 7 when you solve for this. But you have to recognize this as a Pythagorean triplet. That is, you have to know some basic triple Pythagorean triangles that are right triangle. And the Pythagorean triplets, if you remember, are these 3, 4, 5. That forms a right triangle. 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, and 17. See, if you're given this, ST is tangent to circle O. First, the student would have to recognize that if it's tangent, then this is a perpendicular intersection over here, and this is a right angle over here. Then immediately you have a right triangle, and you always start looking for those Pythagorean triples. And the ST is 24, and that should be a trigger number over there. So that's 24, and then R, the radius of the circle, is 7. So the student starts labeling this. Okay, here's a 7, that's this, and then they start going like, oh, that's 7 over here. But the question is asking, what is the measure of RT? That is, what's the length from here to here? So the question is not asking for the whole length. The question is simply asking for this length over here, RT. Well, the answer is approached. The approach to the answer is the same. This is a Pythagorean triple, or you can use the Pythagorean theorem to solve for OT, and that's OT is going to be 7, 24, 25. And then knowing that this is a radius, that's 7, and you can subtract 7 from 25 to get the remainder of this, and that's going to be 18. So as you can see, many questions come from these basic theorems. So in conclusion, we learned 2 theorems today. The first one was about the line being tangent to a circle. A line is tangent to a circle if and only if the line is perpendicular to the radius at its endpoint on the circle. And that was a bidirectional statement, if and only if. The second theorem that we learned concerned 2 tangent segments. 2 tangent segments. So tangent segments from a common external point, in this case x. These 2 tangent segments are congruent. And I suggested to you many questions can be made using these 2 simple theorems. And I gave you a couple of examples over here. And I suggested whenever you have right triangles, you must go back and rescue the knowledge that you have about right triangles from before. The Pythagorean triplets in particular, then the 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17. These must be absolutely memorized, etched in in your mind. The other part of the questions that can come from these two theorems relate to 30, 60, 90 triangles and 45, 45, 90 triangles, which also lend themselves to easy questioning. Inshallah, we'll have the opportunity to do those in the future. Until then, as-salatu was-salam wa rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.